Einstein's greatest discovery wasn't relativity. His greatest discovery was this. Past, present, and future all exist at the same time. Right now, dinosaurs are still living. The death of the sun has already happened, and your birth hasn't occurred yet. All simultaneously, because time isn't what you think it is. This claim sounds nuts. I know. Everything goes against your gut instinct, because you picture time like a river, flowing from past to future, an unstoppable current. The past is gone, history. The future hasn't arrived yet. And now, this moment, is the only slice of reality. But this is time's biggest illusion. Time doesn't flow. Time just exists. Past, present, and future are all equally real, equally present. Einstein explained this with his block universe theory. The universe is like a four-dimensional block, 3 space dimensions, 1 time dimension, and every part of this block is equally real. Close your eyes now and picture this. You're watching a movie frame by frame. Pick up that film reel. Inside that reel, every frame from beginning to end exists. The first minute's there, so's the last minute. They're all present in that reel simultaneously. The universe is the same way. The Big Bang's there. The sun's death too. Dinosaurs and future civilizations, all existing in this four-dimensional block at the same time. So why do we feel time flowing? Because our consciousness moves through this block. Just like watching that film strip, we can only see one frame at a time. But in reality, all the frames are there. We just experience them in sequence. By the end of the 19th century, physicists believed time was absolute. In Newton's universe, time flowed equally for everyone and everywhere. 1 second in London, 1 second on Mars. At the galaxy's center, at the universe's edge, time was an unchanging universal metronome. Then Albert Einstein came along and changed everything. In 1905, he published special relativity theory, and at the center of this theory was a shocking claim. Time changes based on speed. The faster you move, the slower time passes for you. This wasn't just theory. It was an experimentally testable prediction, and it really got tested. The twin paradox experiment showed this. Picture 2 identical twins. One stays on Earth, the other takes a trip on a spaceship traveling close to light speed. For the twin on the spaceship, time passes slowly. While he lives 1 year, the Earth twin lives 10 years. When the spaceship returns, the space-traveling twin will be younger. This isn't just a thought experiment. It's real physics, something we observe in particle accelerators. But this was just the beginning. Einstein's next discovery was even more mind-blowing. Gravity also affects time. In 1915, he published general relativity theory. According to this theory, gravity is actually where space-time gets curved, and this curvature changes how time passes. In a strong gravitational field, time passes slowly. In a weak gravitational field, fast. This means your feet are older than your head, because your feet are closer to Earth's gravity. The difference is tiny, but measurable, detectable with atomic clocks. GPS satellites have to account for this effect. 12,400 miles above ground, gravity's weaker, so time passes faster on those satellites. The difference is 38 microseconds per day. Might seem small, but if this correction isn't made, the GPS system would be off by miles within days. Now let's go even further. Black holes are the most extreme bending points in space-time. Near a black hole, time almost stops. As you approach the black hole's event horizon, time slows down for someone watching from outside, slows down, then stops. That person sees you frozen at the event horizon forever, but from your perspective it's different. For you, time passes normally. As you fall into the black hole, you experience time normally, until tidal forces tear you apart. 2 different time experiences, 2 different realities. Which one's correct? Both. One of Einstein's most shocking predictions was this. Simultaneity is relative, meaning which events happen at the same time depends on what reference frame you're in. 2 events that are simultaneous for you happen at different times for someone moving fast. Think about it like this. Explosions happen simultaneously in London and New York. Simultaneous for you. But someone watching from a spaceship going near light speed sees one first, then the other. Which one happened first depends on the observer's speed. There's no universal now. This means events in distant galaxies could be in your past, your present, or your future. It's totally a matter of perspective. In one corner of the universe, dinosaurs might still be living. In another corner, the sun might already be dead. Time is a local phenomenon. Hermann Minkowski, Einstein's teacher, summarized this situation like this. From now on, space and time will fade into shadows. Only their union as space-time will preserve reality. Space and time aren't separate things. They're a single fabric called space-time. To picture this fabric, think about this. Earth's surface is 2-dimensional, but it's actually curved in 3-dimensional space. Same way, The three-dimensional space and time we experience are actually part of four-dimensional space-time. And this space-time can be bent, stretched, and rippled by mass and energy. One of Einstein's boldest predictions was gravitational waves. Rapidly rotating massive objects create waves in the space-time fabric, just like ripples when you throw a stone in a pond. These waves travel at light speed and bend space-time wherever they pass. For 100 years we couldn't detect these waves. They're too weak. But in 2015, LIGO detectors caught the first gravitational waves. Waves from two black holes colliding 1.3 billion years away. Space-time itself was vibrating. Einstein was right. This discovery was revolutionary, not just for physics, but for our understanding of time. Because gravitational waves are messages from the distant past. That black hole collision happened 1.3 billion years ago. But that past event is still affecting space-time. The past keeps shaping the present. Now let's get to an even deeper question. Is time travel possible? Einstein's equations don't prohibit such a thing. Actually, some exotic space-time geometries allow time travel. Wormholes, Tipler cylinders, Gödel universes, all mathematically valid solutions. But practically, time travel is super problematic. Like the grandfather paradox. What happens if you go back in time and kill your grandfather? Then how are you born? How do you go back in time? These kinds of paradoxes raise deep questions about time's nature. Some physicists suggest the universe works to prevent these paradoxes. Stephen Hawking's chronology protection conjecture. The universe might have mechanisms to prevent time paradoxes from forming. But this is still an open question. Quantum mechanics makes time even more complex. In the quantum world, particles can be in multiple states at once, like Schrödinger's cat. The cat can be both dead and alive simultaneously, until a measurement is made. This raises questions about time's quantum nature. Maybe time's also in quantum superposition. Maybe multiple timelines exist simultaneously. Multiple universe theories suggest this. With every quantum measurement, the universe splits in two, infinite parallel timelines. According to these theories, infinite versions of you are living right now, each in a slightly different timeline. All these versions are equally real, all experiencing now equally. Time isn't a single line, it's an infinitely branched tree. From a cosmology perspective, time gets even more mysterious. Did time exist before the Big Bang? Stephen Hawking says no. Time started with the Big Bang. There's no before the Big Bang, because time hadn't been created yet. But this leads to paradoxes too. What triggered the Big Bang? If there's no time, how do cause-effect relationships work? Some theories suggest a cyclic universe. Big Bang and Big Crunch cycles. Time in infinite loops. No beginning, no end. From a thermodynamics perspective, time's direction is related to entropy. Entropy is a measure of disorder. According to the second law of thermodynamics, entropy always increases. This determines time's direction, from past to future in the direction of increasing entropy. But this is problematic too. Einstein's equations are symmetric in time. They work forward and backward. So what determines time's direction? This is one of physics's big unsolved problems, the arrow of time problem. One possibility is that the universe had very low entropy at the Big Bang. Since then, entropy's been increasing. This explains how we perceive time's direction. Past is low entropy, future is high entropy. But this explanation's incomplete too. Why did the universe start with low entropy? Was this chance, or is there a deeper reason? The anthropic principle tries to explain this. Only universes that started with low entropy have observers. We're those observers. The relationship between human consciousness and time is also fascinating. How does our brain perceive time? Why do we remember the past but don't know the future? Why do we feel now is special? Neuroscience shows that time perception is the collaborative work of various brain regions, the hippocampus for memory, prefrontal cortex for planning, but we still don't fully understand time's subjective experience. How does consciousness create time? Some philosophers and physicists suggest time is just an illusion of consciousness, like Julian Barber. According to him, only now exists. Past and future are illusions of our memory and expectations, but this isn't satisfying either, because Einstein's equations show time as a real dimension. Time is as real as space. Maybe the problem is in our perception. Maybe real time is very different from what we experience. String theory offers new perspectives on time's nature. According to this theory, the universe is 11-dimensional. The 4 dimensions we perceive are just part of this. The other dimensions are curled up at microscopic scales. Maybe time is also truly multidimensional. Loop quantum gravity is another approach. According to this theory, space-time has an atomic structure, particles at the Planck scale. Time isn't continuous either, it's discrete.
like a digital clock. The smallest time unit is Planck time, 10 to the minus 43 seconds. If time is truly discrete, this changes our understanding of time's nature. Time isn't a continuously flowing river. It's a film strip of discrete frames coming one after another. Each frame lasts one Planck time. Now let's bring this to a personal level. How do these facts affect your relationship with time? If you accept what Einstein showed, past, present, and future exist simultaneously. This means your lost loved ones are in a sense still living. The times they lived still exist.
This can provide consolation, but it's also disturbing. If the future already exists, is there free will, or is everything predetermined? This brings up the old philosophical debate between determinism and free will. Quantum mechanics might offer hope here. Quantum uncertainty might prevent complete determinism. Maybe the future isn't determined. Maybe it's constantly being created through quantum measurements. This might open up space for free will. Aging also looks different from a time perspective. Biological aging is increasing entropy. Disorder increases in our cells. DNA damage accumulates. This also follows time's thermodynamic arrow, increasing entropy from past to future. But theoretically, if entropy could be decreased, could aging be reversed? This is speculative but interesting. Maybe future technology could control thermodynamic processes, slow down aging, maybe even reverse it. The relationship between time and memory is also fascinating. Our memories shape how we perceive time. Nostalgia idealizes the past. Anxiety darkens the future. Depression gives the feeling that time has stopped. Our mood changes our time perception. People who practice meditation report different experiences of time. In deep meditative states, past and future can disappear. Only now remains. This shows time's subjective nature. Maybe Einstein's block universe can be experienced in meditation. Music also has an interesting relationship with time. To understand a melody, you need to remember past notes and anticipate future ones. Music turns time's flow into art. Rhythm becomes time's heartbeat. Language also shapes time. Some languages don't have future tense. Others have different levels of past. The language you speak affects how you perceive time. Time is not just a physical construct, it's also cultural. Technology's relationship with time is also changing. Clocks mechanize time. Now atomic clocks measure time at the quantum level. In the future, quantum clocks might make even more precise measurements. Time measurement pushes technology's limits. How will artificial intelligence perceive time? Computers already experience time differently. For them, a millisecond might be like hours for humans. A super-fast processor might experience time slowly. This also shows time's relative nature. Space travel will make time even more complex. During trips to Mars, there'll be synchronization problems with Earth. Because of light speed limits, real-time communication is impossible. This reveals time's practical problems. In generational space journeys, the situation gets even more complex. Generations born, living, and dying inside the ship. For them, time is limited to life inside the ship. Time on Earth loses meaning. Time becomes a local experience. At a cosmological scale, time is even more fascinating. The universe's age of 13.8 billion years is from our perspective, but in different parts of the universe, time passes differently. Near the supermassive black hole at the galaxy's center, time passes very slowly. Dark energy is accelerating the universe's expansion. This also affects time's future. Billions of years from now, galaxies will be so far apart that future observers won't even be able to tell the universe is expanding. Time is changing the universe's story. Finally, making peace with time on a personal level. As Einstein taught, past and future are equally real, grieving our losses, but knowing they continue to exist on the timeline, planning the future but accepting that it already exists too. Maybe time's greatest lesson is this: living in the present moment, because every moment we experience is a unique point in the universe's four-dimensional fabric. That moment will remain in that fabric forever. In Einstein's block universe, every moment you live becomes immortalized. Time is much richer, much more complex, much more beautiful than we thought. It doesn't flow, doesn't stop, it just exists. Past, present, future, all simultaneously. This cosmic perspective brings new meaning to our lives, because every moment of ours gets woven into the universe's eternal fabric, and this is time's true nature. Not flow, but existence. Not temporary, but eternal. Not one-dimensional, but part of a four-dimensional tapestry. Einstein discovered this. Now we're learning to live with this reality.